Hi, everyone, and welcome back to another special episode of Learn with Dr. G. That's me. Today, we're going to use machine learning to better impute missing values in data sets, but with an added Toon Squad kind of twist. Let's get started. If you missed the last episode of Learn with Dr. G, I introduced you to a new learning path on Microsoft Learn that was inspired by the new film Space Jam: A New Legacy. You can check this path out by going to aka.ms/explore sports with code. You can check out the short intro to this video at aka.ms/learnwithdrg/basketball/videos. A quick recap on the film. NBA champion and global icon LeBron James goes on an epic adventure alongside timeless tune Bugs Bunny in the animated live-action event Space Jam: A New Legacy. From director Malcolm D. Lee and an innovative filmmaking crew, including Ryan Coogler and Maverick Carter. Today, we're going to dive right into the first module of this new learning path inspired by Space Jam: A New Legacy. The first module we're going to explore will have us use anonymized player data from human basketball players and Toon Squad characters from the film to create a machine learning model that'll help cleanse our data so that we can use that in an app during games in the next module. We're also going to explore bimodal data distributions, all with Python and Visual Studio Code. Let's jump right in. I've already got a little bit of my local environment set up here. What I have is a folder where I have a Jupyter notebook file called spacejam-anl. And I also have already downloaded my CSV file, playerdata.csv. So you can see my CSV files in here, and I've already started on my notebook. I've imported pandas, I've imported my data set, I've taken a look at my data set, and I'm now to the point where I'm identifying some missing values that I want to try to impute. So what I've done so far is call isNA on our data frame. This basically returns us a list that is true or false for every single row. If the value is null or not a number, nan, then it'll return true. And if it is a value, then it'll return false. Then I applied the sum function to this. And what I get back is a table where each column has a number of how many not a number or null values there are in that column. We can see now that there are two columns that have all null values. And if we take a look at our CSV file, we can see that there's these kind of commas here that keep repeating because that's where our two columns with no numbers or no values are. I'm going to go ahead and zoom in here a little bit now that we have seen our file structure. So since we know we have 46 rows and those two columns had 46 null values, we can do something fairly simple to get rid of those missing values. Basically, we drop a column where all of the values are null. It doesn't really make sense to impute those values to try to guess or predict what those values would be because the whole column is null and the names were also unnamed. So I think it was probably just a mistake that those columns were in there in the first place. When we do this, we see that we've gotten rid of those two columns, but we still have a number of missing values. Similar to how we got rid of the columns with no values, we might also have some rows that have absolutely no values. In that case, again, it was probably a mistake to have it in the first place. Maybe a new line got entered on accident, but we want to get rid of those before we do any other calculations. It looks like there was no change at all, and that's because we didn't have any rows that didn't have any values, but it's good to just cleanse that in that way anyways. Speaking of rows and columns that have missing values, sometimes we want to get rid of rows or columns that have a lot of missing values because it doesn't add any information to our data. So for example, if we had a row that only had the ID and nothing else, it wouldn't technically be an empty row, but it's still not useful information as we try to predict different data based on other player data. So one way that we can explore this is by showing our entire data frame. This is pretty okay to do because we only have 46 rows. But if you were going to do this with a much larger data set, you might want to use a different kind of software to just view your data. So as we scroll through this data, we can see that there are a few rows that have the same three missing values at the beginning. Those are the nan values, not a number values. And we can see that points, possessions, and team pace are missing for those players. Now, let's take a step back here and see what we're even trying to predict. Before you just start deleting everything, you should make sure that you understand what your goal is. In this case, our ultimate goal comes in the next module of this learning path, which is to build an app that a coach can use during a game to determine which players should be on the court and which might need to take a break. The way that the coach will determine this is by using the player efficiency rating, or PER. PER for basketball players is often defined by all of the stats for a player for an entire season or their entire career. But we want to try to repurpose that in the next module for during a game. Player efficiency rating is reliant on a number of data points. Points, possessions, and team pace being some of the more important metrics that we use to determine PER. So in our case here, when we have rows that are missing those values, we probably need to impute them or cleanse them out. So what we're going to do is remove any row that is missing more than 12 values, because we know that we want to have at least 12 values in order to have an accurate PER prediction. It looks like we're starting to cleanse our data appropriately because we don't have a lot of missing values at this point. But we've also done a lot of the easy cleansing, meaning just basically getting rid of data that won't be of use for us. The next missing values are going to be the tricky part, because we need to use other information within the data frame or the data set to impute those values. Before we can do that, though, let's make sure our data frame is all cleaned up. What I mean by this is we just removed some rows and some columns. So we can use this reset index function to allow us to make sure that our indices across our data frame go from 1 consecutively and don't have any missing values there. So now we have a total of 42 entries across 14 columns. So I mentioned that we're going to impute some missing values. Now this can be tricky because sometimes we use things like the average of that entire column, but that becomes a problem if you have outliers. So we want to get rid of any major outliers, or at least know about them, because that might affect how we want to impute our missing values. To figure out if we have any outliers, we'll use the describe function, which gives us an overview of all of our columns where we get the count, the mean, the standard deviation, min, max, and everything in between. You can see here, for example, in our points column, that our average number of points is close to 1,600, while our min is 183 and our max is around 2,000. So that min number is really far away from our mean compared to where our max number is. So that min number actually might be an outlier. But we're here in code, so why don't we visualize this real quickly? First, we need to make sure that we have the appropriate libraries, in this case, Matplotlib and Seaborn. And then we're basically going to create a figure to show our standard deviation using box plots. Once this completes, we can see all of our box plots here, and we can see pretty small down here at the very bottom of this points box plot, there is in fact an outlier. It's that little diamond down here at the bottom. This is where you do need to have some knowledge of basketball to determine whether or not this outlier is a mistake or an important data point. In this case, we're gathering data where a player having only 183 points, nearly 1,400 points less than the next person, is pretty unlikely. So we can feel pretty confident that that data point is actually incorrect and therefore shouldn't be included in any of our calculations. But I don't know if you noticed, there was also, it's kind of hard to see, an outlier over in the possessions column as well. So I'm kind of curious if this outlier is the same player or row, or if they're two different ones. We can know that by using the IDX min function, which basically will give us the index of the minimum value of a particular column, in this case, the points column. So the index is index number 35. And let's do the same thing, but for possessions. Yep, it looks like it's the same index. So row 35, or with index 35, is likely the one that we just have incorrect data for and probably want to remove. Just to be safe, we can use the points outlier variable that we created that contains that 35 index to remove that row from our data frame. We want to remove it in place, so then that way we're updating the data frame itself rather than creating a copy into a new variable. And then we're going to print out the last 10 rows. Since we know we only have 42, then we can go up to 32, and that should capture that 35, and we shouldn't see that anymore. Great. So we've dropped that index. We go from 36 to 37, and we don't have to worry about that value messing up any of our calculations. Again, let's go ahead and clean up our data frame by resetting the index. So then that way we don't go from 34 to 36, but from 34 to 35. Okay, let's see where we are with our missing value. It looks like we're missing 6 values from the GP column, 5 from the MPG column, and 9 from the PER, which is the one that matters the most to us. You can get a full explanation of all of our columns on the Learn module, but real quickly, GP stands for games played, and MPG is the average minutes a player has played per game. We know that PER stands for the player efficiency rating, which is calculated through all these other values. So it's probably most important that we impute the GP and MPG missing values first. Let's go ahead and view our data in another way using histograms. This will help give us an idea as to how we might want to impute those GP and MPG missing values. We can see that most of our histograms, aka columns, look like they have a pretty even bell curve or have normalized values. We can take a closer look specifically at that GP column, and we can even apply that line to it to see if that bell curve exists. And we can see that it really is a pretty normally distributed bell curve. Let's actually look at all of our values using that bell curve instead of the histogram. So it looks like something really interesting is happening here. Generally speaking, we do have bell curves for all of our columns, but there does seem to be a little bit of bimodality in some of them. For example, in DRR, we can see this bimodality pretty clearly, and similarly with PER. Some of the other columns are a little bit more subtle, like team pace, GP, or MPG doesn't even look like it has any bimodality. We can look at one of the columns a little bit closer. Let's take points to be able to see that bimodality a little clearer. So we can see there are 2 points on this curve, and they correspond with these 2 high points in the histogram. It looks like around 1600 is where that midpoint is. So I really want to know how many players in our data set have more than 1600 points or are part of this side of our curve. It looks like 23 of our players have more than 1600 points. Okay, so we've got 23 players that have a high points average. Let's take a look at some more data. Another one of our bimodal data columns was DRR, which is the defensive rebound rate. We can view this column with the histogram and curve attached to it and see that it's maybe around 15 where we get that split. So now I'm curious how many players have more than 1600 points and more than 15 rebound rates. So that's narrowed us down from 23 players to 18 players. And we can also take a look at PER. That was where it had a really big bimodal curve. Okay, so around 17, I would say, is where we get that split again. So now I'm looking for the list or the number of players in our data set that have at least 1600 points on average per game, at least 15 defensive rebounds per game, and at least a score of 17 for PER. All right, it actually looks like it is player 31 through 46, with some of our players having been removed, which probably makes sense because the likelihood of this data set being kind of all human players and then all Toon Squad players is a pretty good likelihood. So I think we've narrowed down which part of our data set is Toon Squad and which part is human. So now that we know this information, what we can do is apply some identifier to each row. Here, I'm just going to use player and then a number to indicate a human player, and Toon Squad and a number to indicate a Toon Squad player. So first, I created a list, and then I'm going to add that list as a column to our data frame. It was lucky that our human players were up at the top and our Toon Squad up at the bottom because it made it really easy to make that list in the correct sorted order. So we basically add that player column to our data frame, and then we can do some quick cleanup because it does matter whether a player is human or Toon Squad. The app we're going to build is only for Toon Squad players. So we probably want to reorder this to bring that player column, identifier column, over to the left where we can see it a little bit better. Okay, so we haven't actually imputed those missing values yet. Let's go ahead and remember what they were. 6 from GP or games played, 5 from MPG or minutes per game, and 9 for PER or player efficiency rating. Before we decide exactly how to impute them, let's revisit our histogram and bell curve for GP or games played. And we can see it's a pretty standard bell curve here. Similarly, for MPG, we can see that that is an maybe even clearer bell curve. But remember, for PER, we still have that clear bimodal distribution across our data. So we probably want to do something different for GP and MPG than we do for PER. And this is why we did all of the previous work, identifying any outliers, seeing what our distributions were, because we're going to use the average for the GP and MPG columns to fill all null values within those MPG and GP columns. Because it is a pretty normal distribution, we're just going to use the average of the entire data frame to do this. So we can see that once we do this, all we're missing are those 9 PER values at the very bottom. So we know that PER values are determined based off of a formula that takes into account all of these other statistics. We could run things through that formula, but we could also use a machine learning model to do it for us. So we've written this code here. And basically what we're going to do is leverage scikit-learn. Then we're going to split our data into input as that capital X variable, being all of the statistical data. So we're going to use all of the statistical columns that influence PER, not including PER, for all rows. And our Y or output is going to be all rows, but only that last column, which is PER or player efficiency rating. We're going to use scikit-learn to create a linear regression model. And then we're going to use the cross-val score function from scikit-learn, which takes in our model, our input data, our output data. We're going to ask it to cross-validate our data in 10 folds, which you can learn more about in the module itself. And what we want back is an R-squared score. This is going to help us visualize our output in a histogram. And this is going to create that histogram for us, as well as print out all of the scores that we are predicting. So let's go ahead and run this. And we can see that across 10 different cross-validating training models, we have a pretty good R-squared score of 99 point something, meaning our model is pretty accurate at predicting PER. So next, we're going to fit our input and output data to our model. Then we're going to create a mask of our data, which is basically just going to provide a true value if that row contains any null values and a false value if it does not. What we're trying to do here is identify the exact rows that are missing their PER values. And we already know that PER is the only value that's still missing from our data frame. So we can see here that row 2, 7, 8, 11, etc. all have the missing PER values. Next, we're going to gather those rows specifically. And again, we're only taking those statistical values that will impact PER values. So we can see here a table where we have those same rows that we identified as missing PER values with the statistics that will help us determine the PER value. So we're going to put that all together now. This line is just so incredibly powerful. What we're doing is we are taking our linear regression model that we already trained, cross-validated, and fitted. We're going to predict the PER or the Y value, which we defined as the PER value, for the player DF data frame, but only locating, using our mask, the values that are these statistics, the rows, and only the columns that are the statistics to determine PER. So this part right here is still just gathering this table, right? It's that same bit of code. And we're just passing that table in as our X value to predict to then get out our Y value. And again, we only want to apply it to the columns where we are missing PER. Once we do that, we see that we have no more missing values. And we just used machine learning to impute a missing value. So basically, you don't need to be an expert in how to run that PER algorithm to determine the PER if you have a bunch of previous data from other players. And then you get to use machine learning to do it. Let's go ahead and save this output in a CSV file called player data final, because this now has our cleansed data with all imputed missing values. And we also know which ones are human players and which ones are Toon Squad players. Data science is a lot more than just learning how to use different machine learning models. It also has a lot to do with critical thinking. You need to generally understand how data was collected, how it will be used, and what the relationship between the data and the real world is. And so subject matter expertise can come in really handy. Even if you, as the data scientist, don't have that subject matter expertise, it's important to consult on someone who is a subject matter expert. Furthermore, there are a number of ways that you can impute or fill in missing values. Sometimes it's appropriate to just get rid of those columns and rows completely, and sometimes it's appropriate to use information about the data, like the distribution of it, to determine the best course of action for choosing what values to replace the null values with. And really, that's all, folks. Don't forget to check out Space Jam: A New Legacy, coming soon, to learn how you can use basketball data and machine learning and data science to actually impact gameplay. You can learn more about the film at facebook.com/spacejammovie. And stay tuned for the next episode of Learn with Dr. G, where we will be building that app for a coach to better coach their players using insights gathered from machine learning and data. And as always, don't forget to share your learning successes with me. You can either tag me at Dr. Guthels or use hashtag #LearnWithDrG on Twitter. Happy coding!